All right, this is my chapter 4 original problem. I attempted twice to screen record on my iPad while I worked the problem out, and the screen recording continued to fail, so I'm going to have to do it on paper now again and just re-record it. So I'm not going to go through any of the work here. I'm just going to show you the problem, and then I'll try to write it on paper and show you the process as best as I can. So a piston cylinder device contains, no, I'll do it sideways, and then I'll flip the video. But anyways, a piston cylinder device contains 2 meters cubed of hydrogen at a temperature of 477 degrees Celsius and a pressure of 500 kilopascal. An electric coil inside the device is turned on and provides a 5 amp current from a 240 volt source for 3 minutes. There's also 8 kilojoules of shaft work being done to the system during this constant pressure process. The hydrogen expands and 5 kilojoules of heat is released. Determine the mass of hydrogen in the cylinder, the final temperature in Kelvin, and the final volume. All right. So first, we are going to look for the mass of hydrogen in the cylinder. So for mass, we're going to use the equation of state. So P1 V1 is equal to mR T1. T1 is equal to 477 degrees Celsius, and that's equal to 750 Kelvin. R is given in table A2A, and it is equal to 4.124 kilojoules over kilogram times Kelvin. V1 is equal to 2 meters cubed, and P1 is equal to 500 kilopascal. So M is equal to P1 V1 over R T1. So that's equal to 500 kilopascal times 2 meter cubed divided by 4.124 kilojoules over kilograms times Kelvin. And T1 is equal to 750 Kelvin. Solving for mass, it comes out to be 0.3233 kilograms. Okay, so yeah, that's our mass. That's part A. And now part B was find the final temperature in Kelvin. So from the problem, we have work. We're gonna have work electric coming in, or electric work coming in. So work electric is equal to V times I times delta T. So that's going to equal 240 volts times 5 amps, 3 minutes. 3 minutes times 60 seconds is 180 seconds. And then 1 kilojoule per second over volt is equal to 1,000 volt amperes. Work electric comes out to be 219,000 divided by 1,000. So, I'm sorry, 216,000 divided by 1,000. So that's equal to 216 kilojoules. Now, for our energy balance, work electric in plus work shaft in minus Q out actually minus boundary work is equal to change in energy. Work electric in is 216 kilojoules. Work shaft in is 8 kilojoules. And heat out, heat out was 5 kilojoules. And that's going to be equal, moving boundary work over here, so adding change in energy with boundary work, that's going to be change in enthalpy. And that's also going to equal mass. Wait, what am I looking for? I found mass. I'm looking, yeah, so M times H2 minus H1. And that's also equal to mCp T2 minus T1. So network and Q, like everything on the left side, that comes out to be 219 kilojoules is equal to 0.3233 kilograms. In table A to B, CP, oh, my hand's getting tired. CP is equal at 750 Kelvin for hydrogen. CP is equal to 14.645 kilojoules per kilogram times Kelvin. So we're going to move that up here into this equation. 14.645 kilojoules over kilogram times Kelvin times T2 minus 750 Kelvin. Hang on. Okay. Solving for T2. T2 comes out to be 796.3 Kelvin. So that was part B. And now part C, final volume. P1 V1 over T1 is equal to P2 V2 over T2. P1 is equal to P2. So V2 is equal to T2 over T1 times V1. That's equal to 796.3 Kelvin divided by 750 Kelvin times 2 meter cubed. I had to hold the paper. And that means final volume comes out to be 123 meter cubed. I'm sorry for the inconvenience. I really tried to get this screen recording to work. As you can see, I've worked it out not once, attempting to screen record, and it would not go through. So this was my last resort as it's running late. I hope you enjoyed the video. I hope you found it helpful. And I will include snapshots of this work as well, because I've gotten the same answers and it may be cleaner. Thank you for watching. Please like and subscribe and turn the bell on. Oh, and buy my merch. Thanks.